All right, async week 8. We're moving along. I'm going to talk about improper integrals, and this really follows directly from what we were doing in class. For me, it was last night, L'Hopital's rule. You're going to be using it in some of these examples, not all of them. And in some of the examples, you're going to use the integration techniques you learned throughout the chapter, but not all of them. Some of them are just going to be really straightforward integrals from Calc 1. So let's get started. I'll give you a definition that sort of explains what improper integrals are. There's more than one type. The integrals themselves usually aren't too crazy. Like I said, every once in a while you'll see a technique that maybe would involve integration by parts. You could maybe possibly see, you're more likely to see like an inverse trig function, the occasional trig substitution, maybe one or two at the most, probably in this section. The focus here isn't really the integration itself. It is more so the process of being able to find the value of the improper integral. So let me give you a definition here, and we'll talk about different types of improper integrals and what they mean. And this is really sort of gearing us up for what we're going to be doing in chapter 8, talking about convergence and divergence. It's just a little bit different here because we're going to be focusing on integrals and combining that with what we know about limits. So an improper integral, one or both of the limits of integration are infinite. So that's one type of improper integral. Or f has a finite number of infinite discontinuities in the closed interval from a to b. So we would say, or f has a finite number of infinite discontinuities. Discontinuities in the closed interval from a to b. So we're going to be focusing on both of these instances. I don't think you're going to see anything doubly discontinuous in this section, which means that you're going to have both an infinite limit of integration, maybe two of them, and a finite number of infinite discontinuities. So I really want to focus on talking about how to set these up. And then when we get to the particular examples, I want to talk with you about what this would look like. Because I think it is important to, of course, understand what it is you're trying to integrate. So for infinite integration limits, let me give you a definition for how to deal with this. All right, so you're going to have three different things that could occur. One of them is just if your upper limit is infinity. So we would say if f is continuous on the interval from a, not to b, I'm so used to writing b, from a to infinity. So if this is the case, then we could say that the integral from a to infinity of f of x dx is equal to the limit as b approaches infinity. And you can switch these variables up however you want. I'm just randomly picking a b here for your definition, of the integral from a to b of f of x dx. Now, I've had a lot of issues with students in the past just not writing their limits here. They are like, okay, fine, I'm going to integrate from a to infinity, and then they evaluate it and they take the limit, but they don't write it. You must rewrite your improper integral as a limit. You must. That's not an option. I'm not going to say like, oh, this is fine, just leave it like that and evaluate it. If you're taking a limit, write the limit. If you don't, I'm going to take off points. It's really important that the limit is there. Say what you mean what you say, just do it. All right, the other option is if f is continuous from negative infinity up to b. Then we're looking at something similar in that case. We're talking then about the integral from negative infinity to b of f of x dx. And again, I'm just randomly picking a variable here. Honestly, I don't usually use a and b here for my limits. Usually I'll just use like k, or I mean, you can use m if you want. You pick. But we're going to send a off to negative infinity, and then we're going to replace negative infinity with a. And we'll go from a to b of f of x dx. I'm just using a and b here because that's the way that it was defined here in this definition. Now, in both of these cases, the integral converges, and we'll talk about that if the limit exists, otherwise it diverges. So I'm going to say the integral converges, we'll say converges to a value if the limit exists. Otherwise, it diverges. And like I said, we will kind of talk a little bit more about this when I get to an example when it actually means something to you. Sometimes when I try to explain things in the abstract, I don't think it's that helpful. So we'll kind of talk about what this means in a few minutes. Okay. The other instance that you're going to have here with these infinite limits of integration would be if you had both your lower and your upper limits of integration be infinite. So if f is continuous on the interval from negative infinity to infinity, then we could say that the integral from negative infinity to infinity of f of x dx. All right, now this is going to be arbitrary. You're going to split this up however you want. You're going to choose a real number c to cut this off. And what you're going to do is you're basically going to set up two integrals, one that looks like this, going from negative infinity up to whatever arbitrary value you choose, and the other one is going to pick up back at that same value and go up to positive infinity. I'm just going to call the number c. You're going to just pick a value c. So we're going to go from negative infinity to c of f of x dx. And then we'll pick this back up again at c and then go all the way up to infinity for f of x dx. So remember your rules for integration that you learned back in Calc 1. You learned a bunch of properties. It said that as you know, you could split up the integral for some real number, and as long as we pick it back up again at that number, we haven't actually changed anything. We're just taking the area from one part and adding it to the area from another. That's kind of what you're thinking about here. Now, this is going to be where c is any real number. Okay. Now, in this case, the integral is going to diverge if one of the integrals diverges. So the integral diverges if one of these integrals diverges. And you'll know it diverges because you're going to get a value for your integral of infinity. So if you don't get some sort of real number answer when you integrate and you find the value for this limit, then your integral is going to diverge. It will diverge off to infinity. So if you just have one or more of these diverge, then this integral is also going to diverge. So I'm going to get into this so that you can sort of see how this works and we can kind of discuss what this looks like. Even maybe you can look at some pictures graphically. Example 1. So I'm going to start out with something pretty basic. We're going to take the integral from 1 to infinity of 3 over x to the 5th dx. Now, if you're trying to get an idea of what this looks like, This is our graph from last night. I gotta fix this. Oh, you know what? It's a little dark outside. Maybe I don't need to brighten this all the way. All right, so you'll go 3 divided by x to the 5th. And remember that what we're doing when we're integrating, when we have upper and lower limits of integration, is we're really thinking about the area under the curve. So you might be wondering, like, how could we possibly get a value for the area under the curve if our upper limit is infinity? Wouldn't it just go on forever? In some cases, it will. And in other cases, your area is actually going to converge to a value. If you're looking at 3 over x to the 5th, and we can, we'll zoom standard at first and just try to get some sense of what's going on with this picture. You can see that this graph right now, I know it looks like it's got all these values sitting here on the x-axis, but if you were actually to switch your window out a little bit, let's kind of narrow this in. Even if you wanted to just zoom in, so we'll hit 2, enter. You can see that there's a little bit more space in here than maybe you would have seen previously. But the idea here is to recognize that as these values of x get increasingly large, you're really not including that much more area under your curve. I kind of want to zoom this back out and then switch your window. So I'm going to go back to zoom standard, zoom 6. So let's say we're only looking at what's happening between, let's see, if x is 1, y is 3. Let's just look at this in our window from well, we can have an x min at 0. That's fine. Let's do a y min of 0 and a y max of 3, just so we can get that top value in there. And we know there's a horizontal asymptote at 0, so don't need to go anywhere below the x-axis. I mean, look at what this is doing. It's really hard to tell, but it looks like this is just hitting the x-axis. It's not, but the values are so small. They're so close to the x-axis that you can barely even see that they're positive. You can look at this also if you were to look at your table and see how small these y values are as x gets increasingly large. Now, I still have my table set up from last night when we were looking at extremely large values of x, but 3 times 10 to the negative 5th means you're taking 3 and then moving your decimal over to the left 5 places. And as you continue to increase the value of x, you're moving your decimal to the left more and more places until you get to some number like 0.000000000 25 times 3. So these numbers are really small, very, very small as x continues to get really large. If you think about it that way, you should be getting a sense that if you were to look at the area of this underneath this curve from 1 to infinity, I mean, here's 1. Most of the area under this curve is happening here in this segment from 1 up to 2. That's almost all the area. But once you get past 2, you're barely covering any area under the curve between the x-axis and the curve. There's not much there. And then as you continue to move forward, again, you're not getting much area out of this. It's so close to the x-axis. There's just barely any space there. This is what the whole concept here is to kind of get a sense for, is this integral going to converge or diverge? And if it's going to converge, it means that eventually we're going to get to the point where the area underneath this curve converges to a value, because these values here at the bottom are going to get so tiny and minuscule that, similar to what happens with a limit, you're going to see that they're no longer going to be contributing significantly to the area. So we're expecting that this is going to converge. And when we get to a diverge example, I'll look at that on the calculator too, so you can kind of see. But it's good to have an idea of what you expect to happen before you actually start working on these integrals. So I'm guessing it's going to converge, but we're going to set this up just like we always will with a limit. Now, if you want to follow directly from the definition, that's fine. I feel like you're probably going to vary your variable. I like to use k. My name starts with a k. I don't know if that's why, but I feel like k is a good variable to use. You can use b if you want. You can use a if you want. When I gave you this in the definition, I used b. I want you to feel comfortable using whatever you want. I don't want you to feel like, oh my gosh, I can't remember what variable am I supposed to use. Is it a or is it b? It doesn't matter. When you set this up, all you're trying to do is replace the infinite limit with a variable. So I'm going to call mine k. You can call yours whatever you want. I'm going to send k off to infinity. Now, if k is heading to infinity, I'm going to then go from 1 to k instead of 1 to infinity. This is the only thing you're changing in your setup. You just have to know which piece is changing, which one's staying the same. The 1 stays the same. Infinity gets switched out with the variable. That's it. If the 3 is bothering you, you could even put that in front of your limit. I'm going to just pop my 3 in front of the limit. There it is. And then since you know you're going to be integrating, we can rewrite x to the 5th in the denominator as x to the negative 5th dx. Now you've rewritten this as a limit. You can go ahead and integrate, and then we'll use the FTC and then evaluate the limit. If we need to use L'Hopital's rule, but I don't think you're going to need to in this instance. All right, carry everything else with you. If you feel like you're going to forget the 3, that's fine. Leave it in there. It's totally up to you. I don't want you to forget anything. Hold on to your limit until you're ready to evaluate. And when you integrate this function, you're going to increase the power by 1 and divide by the new exponent. So you have x to the negative 4 divided by negative 4, and that is going to get evaluated from 1 to k. And you can even pull this negative 4 out front if you'd like. Because remember, if you're dividing inside the limit, if it's a constant, you can pull it out of the limit. Up to you, whatever you feel most comfortable with in this case. And then we'll have 1 over x to the 4th from 1 to k. You might even have in your limit, you might have negative 3 over 4x to the 4th, and that's fine. If you don't want to yank it outside, that's fine. Personally, I just like to look at the most simplistic version of the expression that I can possibly find. All right, now we're going to use the FTC, and then we'll evaluate the limit. So first, I'm going to start out evaluating this expression at k, and then we'll evaluate it at 1. So I'm going to keep my limit in here because I'm not evaluating the limit yet. So I'm going to go 1 over k to the 4th minus 1 over 1. So obviously minus 1 over 1 to the 4th, but if you just want to write minus 1, that's fine. You don't need to show me every little teeny tiny thing, just the important stuff. Okay, and now if you'd like, you can go ahead and evaluate this limit. So when you evaluate the limit, remember you're replacing k in this instance with infinity. So you're going 1 over infinity to the 4th minus 1. If we're dividing a constant by infinity, that quotient is heading to 0. And then you end up getting 3/4 as the value of your integral. Negative 3/4 times negative 1 is positive 3/4. And then you would say that your integral converges. This means, as we suspected, that as x gets increasingly large, the value underneath the curve, the value for the area is getting to be so incrementally small that at some point it's not having an effect on your area. It will have this limit that's being applied to it that's sort of making that eventually sort of level out at a specific value. I was going to check your homework just to make sure that we're answering all the questions it's going to be asking you to do. Determine whether the improper integral converges or diverges. If it converges, find its value. We just did that. So we said it converges, and it converges to 3/4. I wonder if remember I showed you how to find a definite integral in your calculator? If we go to second calculate, I don't know if it'll do this for you. Hit number 7, lower limit of 1. So it's asking you for a lower limit. Type in 1. And then upper limit. Yeah, there's no way for you to add in infinity here, I don't think. I mean, there is technically an infinity button. I don't remember where the best shortcut is for it. Is it in the math? No. I mean, I can go find it, but This calculator might not even handle infinity. But I mean, you could get a good idea if you go back. Sorry, second calculate 7. I can't remember where it is. I'll think about it later and find it. Even if we just went from 1 to an upper limit of 10, you should get an area that's pretty close to 3/4. And you do. You get 0.749. And as you continue to increase this value, let's say you did it again, second calculate, number 7, a lower limit of 1, an upper limit of, let's say, 100, it won't even do it. Wonder why. Maybe it's like too much for the calculator. Maybe I just entered something funny. 1 to, let's say, 20. Yeah, it still won't do it. I think it's too close, maybe. But either way, you could see that if you did 10, 1, I mean, 11 is probably not going to change anything. Oh, is it not doing anything for me now? Oh, that's helpful. No, it'll still do 10. It just won't go past 10. And it has to think about 10. It's kind of like, don't want to do this. Those values are getting so small. But you can see now most of the area that occurs is happening here. Anything that gets added on at the end is going to be just like next to nothing. And you're going to see that this value will eventually converge to 0.75, which is 3/4. To give you an idea of what's happening there with the improper integral. So that's kind of how that works. We rewrite it as a limit, just evaluate the integral as we normally would using the FTC, and then we just apply the limit, see what we get. Let's do another one. This one's going from 1 to infinity, and we have 4 divided by the 4th root of x dx. If this is bugging you before you even put the limit on, you can pull the 4 out if you'd like, and you can rewrite this as x to the negative 1/4 dx, if you want to do that. And just in case you wrote it wrong, if you're putting this in your calculator to get a good idea of what's happening before you go, you could put it in your calculator the way that it appears here. It would have to be x to the 1/4, but you get it. Always doing this with my template. I kind of want my old 83 back, but definitely broken. Okay, so 4 divided by x to the 1/4 power. I'm going to zoom standard for right now, but we are looking at this from 1 to infinity. Okay, now you might be looking at this and thinking like, gosh, this looks really similar to the last one we did. It's just sort of leveling out. Okay, but look at what it's leveling out to, though. If it is leveling out at all, which it's really going to take it a long time to do so. The point is it's going to take it a long time to do so. If you were to look at extremely large values of x here, you would not be seeing the y value get super close to 0 really fast. You've still got a pretty substantial amount of space between the x-axis and this curve. So yeah, technically it's eventually going to level out, but is it going to do that fast enough so that the area underneath this curve is going to eventually become incrementally 0? That's what we're going to find out. And again, you can go to your table if you want, and you can look at these really large values of x. Remember last time we were getting like 3 times 10 to the negative 25th? This time we're still at substantially large values. Even when we're at 100,000, y is still right around a quarter. So this should be kind of something where you're expecting that maybe we're not going to be able to converge just because the values that you're including there are going to be so much larger. So I'm going to give you the math that goes along with that situation that we just discussed. And I'm not going to do this for all of them. I just want you to get a sense for what you're looking at here. All right, so go ahead and apply your limit. I'm going to put the 4 in front of the limit, and I'm going to not forget about it. And again, I'm going from 1 to infinity, so I'm just going to send k off to infinity and integrate from 1 to k of x to the negative 1/4 dx. So this is an important step. Like I said, I know that we just want to go, oh, well, let's just integrate this and apply the limit. You must write your limit. You must. I'm even going to say that on your test. I'm going to say, remember to write your limits. I'm going to put that in the instruction, and still a third of you won't do it. I got to read the instructions, you guys. All right. Anyway, let's go ahead and integrate this, and then we'll use the FTC. I know we also don't like writing our limits because we got to keep rewriting it. You know, there are worse things that could happen to you in this world than having to continually rewrite a limit line after line. All right, I got to get off this soapbox, don't I? Increase your exponent by 1, divide by the new exponent. If you'd like, go ahead and pull this out front. 4 divided by 3/4 is 4 times 4/3. Be careful there. Don't just cancel out your 4s. This 4 is actually coming back up to the numerator. So you're actually going to be getting 16/3 times your limit as k approaches infinity of x to the 3/4 from 1 to k. All right, now notice the difference here. Even before you apply this limit, well, here, I'll do one more step and then I'll say, notice the difference. So you're taking k to the 3/4 minus 1 to the 3/4. Okay, so comparing this to what happened last time you ended up with a k in the denominator. This time, when you integrated, your k comes up to the numerator. That's going to make a huge difference on your limit, because in the last case, we had this ratio where we were dividing by infinity. You're not going to have that this time. And that should be key, kind of leading you into what we're going to be doing in the next chapter, in chapter 8, versus like, why is this integral different from that one? This one converged. This one will not converge for that very reason. So trying to figure out like, what is the relationship between those values such that one of them converged and the other one didn't, just because the exponent was different. All right, so we have 16/3. Go ahead and apply that limit. Infinity to the 3/4 is still infinity. And infinity minus 1 is still infinity. I know students are like, how is that possible? It's infinity minus 1. How is it still infinity if you took 1 away from it? It just is, because infinity is not like some value that you can achieve and then you just take something away from it. Infinity is just this value that keeps continually increasing. So 16/3 times infinity is still infinity. So we cannot actually say that we have a value, because technically we're diverging off to infinity. And I gave you that in the definition. What did I say exactly? The integral converges to a value if the limit exists, otherwise it diverges. Yeah, that's exactly what's happening here. We did not converge to a value. We ended up diverging to infinity. So that's the difference. If you evaluate your limit and you get a real number, then your integral converges. If you evaluate your limit and you get something that's either positive or negative infinity, then your integral diverges. So what you're saying is, in this case, if we were to look at the area under this curve all the way to infinity, we would never be able to actually attain some sort of finite value. We don't level out fast enough, close enough to the x-axis to be able to converge upon a particular value for the definite integral. So that was good. I'm just telling you it was. Okay, let's do one that needs an integration technique from chapter 7. Yes. All right. I'm doing another one of these, like, all my kids are at school for like a solid 2 hours and I'm by myself videos. I should be downstairs watching some sort of trash TV, but it's just not my personality. I'm just here teaching you. And then as soon as I'm done, I'm going to race over, pick one up, go back, pick the other one up like an hour later. It's crazy. I know Tuesday I was like, oh, I should lay on the couch while I have my 2 hours to myself. I went for like a 6.5 mile run, and I was just like, why do I torture myself like this? You guys, it's the hustle. I love this anyway. I actually find that I'm very invigorated when I do this in the morning versus like midnight. And my coffee hasn't even kicked in yet. All right. Lost my example. This is example 3. We're going this time from 0 to infinity, and our function is x e to the negative x over 4 dx. And hopefully you're looking at this and you're automatically thinking integration by parts. Yes. And if you're thinking that, you would be right, because you have a variable in front of your exponential function. So you have the product of two functions inside your integral. One of them is a polynomial function, and the other one is an exponential function. If you'd like, before you even set up your parts, you might want to go ahead and rewrite this as an improper integral so you're ready to go. So I'm going to write this as the limit as k approaches infinity from 0 to k of x e to the negative x over 4 dx. That's all we did. We just put a limit on it and then swapped out k and infinity. That's it. Okay, now, since you know already that you're going to need parts, remember that your linear piece here in this particular instance will be u. U is always going to be the function that has terminating derivatives if possible, if you have one. And this one definitely has these derivatives that will eventually terminate down to 0. So let's see, we have u being x, dv is e to the negative, if you want to call it negative 1/4 x. If you find that to be easier to look at, then do that. Then du will be dx. Now, remember that when you're integrating your exponential function, I think I wrote this down a while ago. If it's e to the kx, I think I've written it down a couple of times, but I want to remind you, e to the kx will be 1 over k e to the kx plus c. So that's what I'm going to use here. So if k is negative 1/4, 1 over negative 1/4 is going to be negative 4. So v is going to be negative 4 e to the negative 1/4 x. And if you remember this, it'll make your integration a lot easier. You won't have to sit there and do a u substitution or anything crazy like that. Okay, now we're ready to do our integration by parts. The only reason I'm really showing you how to do this, because I know that you know how to do parts, is just applying it to a different situation where you now have this limit involved in your notation might look confusing. Remember, we are still going to be evaluating the limit, so don't drop your limit. I guess technically you could work on the integral and pop it on at the end. I'm just worried you'll forget about it. So I'm going to keep mine in there. All right, so we are turning our integral into uv, so negative 4x e to the negative 1/4 x minus the integral. And you know what? Because we have a definite integral here, I want to make sure we don't forget about our evaluation from 0 to k, minus the integral of v du. So v du. Look at that. I used a bracket, assuming I would need a lot of parentheses. I didn't, but it's all right. I had gotten some feedback, not a lot, but some, that it was easier to just wait until the end to evaluate this. So I'm going to hang on to this for a minute so you don't have parts of this in x and part of it in k. Okay, so you'll have negative 4x e to the negative 1/4 x from 0 to k plus 4 times the integral from 0 to k e to the negative 1/4 x dx. And now we're going to integrate this function. And we already integrated this function before. We found that it was negative 4e to the negative 1/4 x. From 0 to k. Look at that. I didn't use brackets that time, and I needed brackets. All right, I'm going to simplify this again. Anytime I start skipping steps, stuff gets lost. Now, I'm not going to write my evaluation here again because I have the same situation over here. So I'm just going to say minus 16e to the negative 1/4 x, and I'm going to take that whole quantity from 0 to k. There's a bracket, and there doesn't need to be a bracket. All right, now I'm going to use the FTC, and we'll use the FTC and then evaluate the limit. So we'll go ahead and get this written in terms of k. So negative 4k e to the negative 1/4 k minus 16e to the negative 1/4 k minus, and then we'll subtract off the two terms that go with your lower limit. When you multiply here by 0, you're going to get 0 for that term. For the next term, e to the 0 power is 1. If you want to write it as 1 now, that's fine. I'm going to keep mine like this for right now. Okay, so we have negative 4k e to the negative 1/4 k minus 16e to the negative 1/4 k plus, and then if e to the 0 is 1, I'm just adding in 16. Now, watch what happens. Anytime I say that, you know it's not going anywhere good. If I were to evaluate this limit as k approaches infinity, be careful here, because you would be getting first negative infinity times e to the negative infinity. I'm going to do this in pieces here. If you let k be infinity, again, you have negative infinity. And then minus 16e to the negative infinity plus 16. Okay. So the 16 part I'm not worried about. This part I'm not worried about. And you guys maybe are like, oh, I have e to the negative infinity. I haven't thought about that in a long time. Well, let me remind you of what your exponential function looks like. It looks kind of like this. Y equals e to the x. Whoops, sorry. There it is. Y equals e to the x. As x approaches negative infinity, the limit of e to the x actually is 0. So if you want to make a note of that, we'll put a little box around it. The limit as x approaches negative infinity of e to the x is e to the negative infinity, which is 0. Okay. It's not necessarily something I want you to memorize, but it's something that you're going to use a lot. So I want you to be able to find it. I mean, you can technically memorize it, I guess. This is a very important result that you're going to use a lot. Okay, so e to the negative infinity heads down to 0. So you have this limit here on the x-axis. So you have a 16, you have a 0, but this part is the problem. This is going to be negative infinity times 0 minus 16 times 0, fine, plus 16. So 16 times 0 is going to 0 out. The 16, I'm not worried about. It's this part that I'm worried about. Remember when I gave you your indeterminate forms yesterday? Somewhere amongst my insane amount of notes. I'm going to remind you. Ugh. 0 times infinity, other indeterminate forms. I have students who get to the bottom here and they're like, ugh, I don't want to do L'Hopital's rule. Let's just pick one. It's either infinity or it's 0. Let's just pick one. That's not how this works. You don't just get to decide. There's a process. So don't worry about these two terms. We've already found that these two have finite limits. This one is 0, this one is 16. We need to focus on this term. So we're going to focus on finding the limit as k approaches infinity. And remember, if we're going to use L'Hopital's rule, we want to write this as a quotient, but we can leave the negative 4k in the numerator if you want. I'm even going to pull out the negative 4. And then leave the k in the numerator, and then e to the negative 1/4 k can go into the denominator as e to the positive 1/4 k. Now, if you were to evaluate this limit, by the way, I'm just pulling out this one right here. This one we said was 0. This one was 16. It's this one I'm focusing on. If you were to evaluate the limit right now, you would get infinity over e to the infinity. Well, e to the infinity is infinity. You can add that into your limit as x approaches infinity of e to the x is e to the infinity, which is infinity. You can tell that that is happening with your graph. Feel free to also highlight that as a very often used result. So if you would like, we can say this is negative 4 times infinity over infinity. We need L'Hopital's rule. It's also indeterminate. Of course it's indeterminate. It was indeterminate before. You didn't use L'Hopital's rule. It's still going to be indeterminate. But we're going to take the derivative of the numerator and the denominator separately. So the derivative of k is 1, and the derivative of e to the 1/4 k is 1/4 e to the 1/4 k. Instead of, when we're integrating, we multiply by 1 over k. When we take the derivative, we're just using the chain rule, which means we're just taking the derivative of e to the u and multiplying it by u. So chaining on the derivative of the inside function. But this time, because your numerator is a constant, we're going to be able to get a value for the limit. So you're going to end up getting e to the infinity, which is infinity, times 1/4, which is still infinity. And remember, when you take a constant and you divide it by infinity, your quotient is heading up to 0. And then you get a limit of 0. So now you can say that this limit works with that term. So you're sort of looking at each term separately. A lot of times, only one of the terms will end up needing L'Hopital's rule and giving you an indeterminate form. But now we've used L'Hopital's rule. We were able to simplify that down. We got a limit of 0. So now we can go back to our limit up here. Sorry, I've got like arrows upon arrows upon arrows. And we can say that this is 0 minus 0 plus 16. And that means that our improper integral actually converges to 16. So that's cool. Would you like to look at this on our graphing calculators? Of course you would. Of course you would. Okay. Let's do that. I'm kicking myself because I had one just like this that went from negative infinity up to a constant. And I did this one instead. Oh, well. Doesn't matter. It's the same exact process. This is going to be x times e to the negative x over 4. And you can kind of see now that, yeah, your graph is technically going up, but then it starts to head back downward. And if you look at the values of your expression as x gets increasingly large, okay, your calculator says 0. It's rounding. It's not 0, but it's so close to 0 that your calculator is just giving up and being like, okay, 0. I bet you if you hovered over it, oh, It still says 0. It's not actually 0, but those numbers are changing so rapidly. They're getting so close to 0 that your calculator's kind of just checking out. So that's what's happening there. And let's say even if you tried to calculate the area from 0 to 10, let's say, number 7, lower limit of 0, upper limit of 10, you'd probably get pretty close to 16 right there. 11.40 something. Do it again, number 7, lower limit of 0, upper limit of, let's say, 20. It's too close now. It's saying no. Lower limit of 0, upper limit of, let's try 15. No, it just really doesn't want to do this for me anymore. Lower limit 0, upper limit 12. I wonder why. Maybe it's my window. Maybe if I'm not past 10 in the window, it's just like, nope, your window's not good. Now I'm curious. Set my X max to 20. Let's do that. And then we'll do it again. Yeah, maybe it needs to actually have that on there. I probably should have read the error message more closely. I'm just so used to making assumptions with these error messages. Going from 0 to 20. There we go. Mystery solved. And look at that, 15.353157. So even just going up to 20, not all the way to infinity, but up to 20 gets us so close to the value that we converge to. You can see now as you continue to head out, this just such a small bit that keeps getting added and added and added in each time to the area under your curve. You guys, I love this. I love this. I just love this. I don't like being the only one. I hope I'm not the only one. Okay, what else do I have for you? Let's see. Oh, yes. This is good. Good stuff. Okay, so let's do one that has an infinite lower and upper limit. Example 4. We are going to go from negative infinity to positive infinity. We're going to look at 4 over 16 plus x squared dx. Now, I hope that when you're looking at this, after everything you've done so far in chapter 7, you're thinking like, this looks very inverse tangent-ish. And you'd be right. I'm going to say recall, because you know I love that. Du over 1 plus u squared is the inverse tangent of u plus c. So we're very close to that. We're going to rewrite it, of course. First, let's pop our limits on. And I'm saying limits because you're going to need more than one of them. Notice that in this case, you have both upper and lower limits that are not finite. So we are going to start out going from negative infinity up to some value c that we choose. And then we're going to go from c all the way up to positive infinity. And we're going to write this twice. Now, you decide where you want to cut this off. I'm going to pick 0 just because 0 seems like a really great place to cut it off. But you pick any real number c that you'd like. If you want to use c equals like 4 or 1 or anything, do that. But just remember that it's going to eventually get involved in your FTC. So pick something that you actually want to evaluate with, not like 100,000. That would be ridiculous. So I'm going to go from negative infinity to 0. I'm going to do a rewrite twice here so you guys get a really good sense of what's happening. And then I'm going to pick it back up again and go from 0 to infinity. And remember, I'm doing this because I have an infinite upper and lower limit. If I need to remind you, I gave you a definition where this situation occurred. It was number 3. We're just going to chop it off at some real number c. And then pick it back up again. All right, so what this means is I'm going to take the limit as k approaches, in this case, negative infinity. And then I'm going to go from k to 0 of 4 over 16 plus x squared dx. And then I'm going to need a different variable for my next integral. I don't want to use k twice because I'm sending k to negative infinity. If I then send k to positive infinity, it's going to look really confusing. So let's take the limit as, you can use m if you want. You can use, p is a little tricky sometimes. Maybe I'll use m. I'm going to send m off to infinity, and we'll go from 0 to m. Now, you're going to have to evaluate this. So you might want to get it rewritten into the perfect form, and that's what I'm going to do next. So side note, or I'm going to say side work. I want to turn this 16 into a 1 so I can match this up with my formula. So I'm going to divide by 16. Four divided by 16 is 1/4, and then I'll have 1 plus. If I want this quantity to be squared, I'm going to square root the 16. So if I know if I take x and divide it by 4 and square it, I will get indeed, when I square the numerator and denominator, x squared over 16. All right, it's perfect now. We can pop it back in. The 1/4, though, I'm going to put in the front. And I'm even just going to put it in front of, I was going to say I'm going to put it in front of the whole thing, but I'm worried it's not going to get multiplied in. So I'm going to put it in front of each limit individually. So I'm going to rewrite my limits here. I know, all the rewriting. It's going to be okay, you guys. We're going to say dx over 1 plus x over 4 quantity squared plus, and again, I'm taking my 1/4 and just putting it in front instead of putting it in the numerator. M goes to infinity, 0 to m of dx over 1 plus x over 4 quantity squared. So, this is just the same. I haven't changed anything. I've just rewritten it in a different form just by dividing each term by 16. Really, that's all we did. Now we can go ahead and integrate, and then we'll use the FTC, and then we'll evaluate the limits. And hopefully we won't need L'Hopital's rule. One never knows. 1/4 times the limit as k approaches negative infinity. And remember that we are using this formula as long as we are in this form. We're going to use inverse tan u plus c. In our case, we're going to let u be 1/4 x because that's the quantity that's being squared. And then du is going to be 1/4 dx. 4 du is dx. So if you even want to rewrite this one more time, I know you do. I'm just kidding. 4 du over 1 plus u squared. And then you can just go ahead and use the inverse tangent of u when you integrate. All right, so the 4 and the 1/4 are going to cancel out when you do this, and you're just going to end up with the limit as k approaches negative infinity of the inverse tangent of u, and our u was 1/4 x. And then we're going to take that from k to 0, and then plus the limit as m approaches infinity. I said arctan, but we've been using inverse tan notation. It does not matter. I understand your notation, but I want to be consistent with what I use. Inverse tan 1/4 x from 0 to m. All right. We did use an inverse tangent very briefly with a limit when we were working with L'Hopital's rule. Other than that, you haven't worked a whole lot with inverse tangent values in this class. So this will be a good experience for you. So this is going to be the inverse tangent of 0 minus the inverse tangent of k over 4. Do something similar for your next limit. This is going to be the inverse tangent of m over 4 minus the inverse tangent of 0. Now, the inverse tangent of 0 is 0, because remember, when you're looking at an inverse function, the inverse is your angle. So you're saying that you're looking for the tangent such that the value of your angle is 0. So if inverse tangent 0 is your theta, then in this case, your angle is your inverse tangent, which is 0. You can also put that into your calculator. I believe this one we also looked at last night. So the tangent of 0 is 0, therefore your inverse tangent of 0, 0. All right, and then the other two we're going to look at, I'm going to separate them off so that we can just focus on them without having to worry about the extra noise. So this is going to be, if you want to leave the negative on it, I kind of want to make the limit negative. I'm going to make my limit negative. That might come back to haunt me later if I forget about it. So we're going to look at these two limits. Now I'm going to focus on them so I don't need to worry about anything else. Okay, so for your inverse tangent, let's see, and because this one's negative and that one's positive, I'm going to switch them. But basically, I have the inverse tangent of infinity over 4 minus, because I have this negative sign here, the inverse tangent of negative infinity divided by 4. In order for you to actually find these inverse tangent values, you have to know something about the way that your inverse tangent is defined. Simplify this out a little bit so that it just looks better for you. You're looking for the angle whose tangent value is infinity. Now, if you'd like, you can even graph your tangent function. Let's see, tangent x. And I'm going to zoom 7 for zoom trig. When you zoom trig, unless your zoom trig is always going to be standard in this way. Your first tick will be pi over 2, and then of course pi, 3 pi over 2, 2 pi. This is your tangent function. So if you're looking for theta, so this is like find theta such that tan theta is infinity. This is what you're looking for. And you might be wondering, like, how would I possibly find this? I'm ending up getting infinity no matter what. Well, the way the inverse tangent function is defined, which you talked about in trig, is that the tangent of pi over 2 will go all the way up to positive infinity. I'm trying to figure out, I think there's definitions in your book. But when you're looking at the inverse function, you're only talking about this small segment of the graph. And I'm gonna window this out for you, actually. We're gonna go from an x min of negative pi over 2 and an x max of pi over 2. So that'll be the domain for your inverse tangent function. Maybe I should say the range for your inverse tangent function. And then you could graph that piece. Essentially, this is the graph that you would be looking at. Because remember that in order for it to be a function, you have to be able to pass the vertical line test. and then to be an inverse function, you'd be looking at the horizontal line test, and you could only have one of these pieces if you were going to be passing that test. Otherwise, you'd be hitting every single portion of that every time you drew your horizontal line through. Either way, your tangent value that's heading towards infinity has an angle of pi over 2. If you are working with tangents often, that's something that you will remember and note. If you would like, you could graph the inverse tangent function. I guess I didn't even think to do that. I just never graphed the inverse tangent function. If you find it helpful to look at it that way, again, if you want to do a 7 zoom trig, you can do that. But your inverse function is just going to be reversed. Remember, there's that relationship between your original function and your inverse such that they're reflective about the line y equals x. But if you're looking at y equals the tangent of x, y equals inverse tangent of x, you're going to get that flipped variation of the graph. So if you're looking for, well, I guess it's actually a little bit harder to see here anyway, just because of the values that you're getting for y. Yeah, you might want to stick with just looking at your tangent graph. But you can see as x gets increasingly large, heading up towards infinity, this value of y is heading towards pi over 2. I don't know. I feel like it's easier to look at the tangent graph versus the inverse tangent graph. But such is life. You're going to see something happen in the other direction, however, if x is approaching very small values, -10, -100, -1,000, -10,000, you're going to see these values for y approach negative pi over 2. And that's something that you can see on the graph as well. So your inverse tangent for infinity is pi over 2. Your inverse tangent for negative infinity is negative pi over 2. And you can see that if you were to graph this, you're actually looking at y values that are heading out to negative pi over 2. If you were to go back to your original tangent function and look at tangent x, back to our window, you'd have to focus on the window from negative pi over 2 to pi over 2. Yikes. And then you could see that graphically as well on your regular old tangent graph. So as you approach negative pi over 2, the y value approaches negative infinity. That's what you're looking at here in reverse. Am I too bright? Yeah, too bright. It's getting darker outside apparently. So if you have questions about that, you can let me know. But essentially, you're taking pi over 2 plus pi over 2. 1/2 plus 1/2 is 1. You're getting pi. So this is, I mean, it's a trig thing, but unfortunately, a lot of students don't really grasp inverse trig functions when they're in trig. So this converges. So interesting though, because you had this integral that originally was from negative infinity to infinity, and you were probably thinking like, how the heck would something like this ever converge? Well, if you're thinking about that space as x gets increasingly large or increasingly small, you're probably covering a really, really, really small area. Most of the area is happening in the center. And notice, by the way, that it did not matter what value we chose, but choosing 0 here, I like 0 just because it's easy. Choosing 0 here was a good idea because we already knew the inverse tangent of 0. However, if you cut your function off somewhere else, like let's say at 1 or at 5, you would still be getting finite values here. So they wouldn't be 0, but eventually you would get opposite values, and they would have canceled each other out. So they wouldn't have actually affected these two limits. They would have just been opposites, just because the tangent function is an odd function. So we got lucky here that we chose a nice value that worked well for us. Okay. Let me see what else I have in store for you. What kind of excitement lies ahead? I have for you a different kind of improper integral. So we defined improper integrals as having one or both of the limits of integration finite. And we talked about one of them being finite, and we talked about, or I'm sorry, not finite, infinite. We talked about one of them being infinite, and then we talked about both of them being infinite. Now we're going to focus on F having a finite number of infinite discontinuities. So I'm going to give you a definition for that now. We are no longer going to be focusing on what happens if our upper or lower limit is infinite. Let's see. If F has a finite number of infinite discontinuities. If F is continuous, if F is continuous, on the interval from A to B, where B is open and A is closed, with an infinite discontinuity at B, an infinite discontinuity, remember, we would consider to be something like a vertical asymptote. Then the integral from A to B of f of x dx is equal to the limit as C approaches B from the left of the integral from A to C of f of x dx. Now, again, the C is arbitrary. You pick your variable, but the most important thing to note is that you're going to be replacing this infinite discontinuity with that variable. So if we have the vertical asymptote at B, then that's what we're going to replace, and we're going to take our limit and send that variable off to B. And the reason we're approaching from the left is because B is would be the right endpoint. So this is it's open, but we can only approach B from the left if we're inside this interval because B is on the right. We're going to switch that for the next scenario. If F is continuous, and this time A will be open and B will be closed with an infinite discontinuity at A, then the integral from A to B of f of x dx, different scenario here. This time we're going to replace A with C, and we're going to approach A from the right. And then, of course, A was on the bottom, so we're going to switch that out with C on the bottom, which I know seems weird if you're thinking about this alphabetically. You're going to pick your own variable anyway. All right, so that's what we're going to do there. And then the other scenario would be if you had some sort of infinite discontinuity somewhere inside your interval. So these cases cover situations where you're integrating up to an infinite discontinuity, but everywhere inside the interval would be continuous. Case 3 would be that you're just integrating right over an asymptote. So this would be F is continuous on the closed interval from A to B. Is if F is continuous on the closed interval from A to B, except C. Now C is inside the open interval from A to B. So this notation, it looks like a little E. This just means like it's inside the set of. So C is just some value inside the open interval from A to B, where C is infinitely discontinuous. Then what you're going to do is you are going to split your interval up at C and look at each situation separately. So you're going to take the integral from A to B, and then you're going to break it apart at C. So this is different than the situation where we were integrating from negative infinity to infinity, and we had to pick a random value to chop off our integral. This time the value is not random. We're going to chop it off at the infinite discontinuity and basically do a combination of what you're seeing here in steps 1 and 2. So you're going to go up to C, up to your discontinuity, and then from the discontinuity back up to B to the end of the interval and do it that way. And then each one of these intervals would give you a specific case. So this would be like number 1. And then this would be case 2. Because in this case, your upper limit is an infinite discontinuity. Upper discontinuity, and this would be the lower discontinuity. So this would be that case. And then number 1 would be the uppercase. You'd be looking at those 2 limits separately. We'll do one in an example. I would hate for you to feel like you didn't get to see it happen. Okay. I think it's example 5. Okay, example 5. We're going to take the integral from 0 to 12 of 9 divided by the square root of 12 minus x dx. Okay, now these are tricky, not because the process for finding the integral is tricky, but because it doesn't look that weird to you. When you first see this problem, you're just like, okay, fine, Calc 1 problem, it's just FTC. And then it's not until you go to evaluate it and you realize you're dividing by 0 that you realize something's wrong. So it's tricky. It's very deceiving. If you see something like this, think about what's happening with your limits of integration. And in this case, you're going to know right off the bat that it's an improper integral, but you're going to see why when we start actually working on this one. So it is, the discontinuity is occurring at 12, and yes, you will at some point have a variation of this in your answer, so it does matter. All right, so let's go ahead. I thought maybe we should look at this on our calculators. Let's look at it on the calculator real quick, just so you can see what's happening. This is 9 divided by the square root of 12 minus x. And then I'm going to zoom standard again. I guess we're only going from 0 to 12, so that was really all we needed to look at. So maybe let's adjust our window to go from x is 0 to x is 12. And graph it here. Okay, now there's an asymptote at 12. If you have a hard time seeing that, take your window out instead, maybe to 20. Now, you're not actually seeing a piece of this pick up, and that's because you're looking at a radical function, and a lot of times you're only going to see this one wing with the radical function. But what you're trying to do here is you're trying to look at the area under the curve from 0 to 12, and at 12, you have this vertical asymptote, or this infinite discontinuity in the graph, and when you're trying to integrate at this endpoint that's not really creating this finite piece, that's where you need to incorporate your improper integral techniques. Because at 12, notice that if you were to divide by 12, you'd get an error. You can also see that in your table. Any value, of course, that would be greater than 12 would give you an error. So 12 gives you an error because the function doesn't actually exist at 12. It does exist for 11.999, if I'm taking you back to Calc 1, but look at how large that value is starting to get. 11.9999, now we're at 900. So, and your calculator just assumes we're talking about 12 at that point, but we're really here. So these values get increasingly large, and your question is like, can we actually be able to figure out if this converges to a specific value? I mean, looking at how large this number gets, I would imagine that, like, yeah, probably it increases so rapidly that that would be my guess. If it increases slowly, then you might be thinking maybe it doesn't converge to a value. But this is pretty rapid. So let's go ahead and set up the integral. You know that 12 is the problem. 0 is not a problem. If you're just thinking about this function and you were to take 12 minus 0 and square root it, no big deal. You can do that. It's the 12 that's the issue. So you're going to set up your limit, and you're going to take whatever variable you want and send it off to 12. And then we're going to go from 0 to k. Oh, and I'm going to approach 12 from the left. In most cases, it won't matter, but in some cases, it really will make a difference. So we can only approach 12 from the left. Our function doesn't exist for values to the right of 12. So we're going to go from 0 to k. If you want, you can put the 9 in front of your limit. And then you can just write dx over the square root. Oh, you know what you might want to do, actually? This is just going to be a standard u substitution. You can just write this as 12 minus x to the negative half dx. Maybe do that. Just a thought. And then if you let u be 12 minus x, du is going to be negative dx, and negative du will be dx. All right, so you're going to have negative 9, that's from your negative du, times the limit as k approaches 12 from the left, and then you're going to take u to the positive half, divide it by a positive half, which means you're multiplying it by 2. Sure, we'll just plug it back in the next step. Actually, if you want, we'll even multiply this out. 2 times 9 is 18. It's still negative because I had this negative du. And then I have 12 minus x to the 1/2 power. Means we'll just put it back under the radical again and go from 0 to k. Okay. Now we're ready to use the FTC. So we'll have negative 18 times the limit as k approaches 12 from the left. We have the square root of 12 minus k minus the square root of 12 minus 0, which is just 12. All right, now as we are approaching 12 from the left, you're going to see that these values will actually, I mean, it doesn't matter which way we approach it. If you plug in 12 for k, 12 minus 12 is going to give you 0. So you're going to have 0 minus the square root of 12. And then you'll have 18 times the square root of 12. I don't know if Achieve wants you to simplify that. I doubt it because I know how they are. But split 12 up into some perfect square factors. 4 times 3, the square root of 4 is 2. You'll still have a 3 left over. And you'll have 36 times the square root of 3. And you will find that the area does indeed converge. We did not actually try to calculate that. I believe I'm up to 20 now, so we should be able to. But if you hit number 7, lower limit of 0, right, 0, yes, upper limit of 12. It's thinking about it. See what it decides to do. it says approximately 62.35. So the square root of 3 is like what, 1.7-ish. So yeah, that sounds about right. 62.35, 36 times the square root of 3, 62.35. So your calculator knows what it's doing most of the time, if it can handle what you want it to do, all the demands that you give it. Okay, so that's an example of an infinite discontinuity. Let's see what else I was going to do. I was going to do another one that needed L'Hopital's rule, just because I thought that would be a good thing to go over. And then maybe like another inverse trig one, because I thought that would be good to go over. And then was I going to do a doubly no, I was going to do one that had a discontinuity in the middle. All right, so I have 3 more examples I want to do. I only have time for one right now before I have to go back to tree school pickup. I have to add this on, but that's okay. Example 6. I mean, technically, I don't have to do the inverse trig one. I just thought it would be helpful for you. Let's do this one. We're going from 0 to e of the natural log of x squared dx. We talked about this yesterday. Anytime you see the natural log of x squared, it's probably going to be most beneficial to you to write that as twice the natural log of x using that power rule for logarithms. And then you might want to put the 2 in front of the function, just because sometimes it's just helpful to only have to focus on your actual function without any extra hoopla in there. Okay, so the natural log of x dx, and again, right now you're looking at it and it just looks like a Calc 1 integral. The problem is the natural log of x isn't defined at 0. If you are not sure, look at this on your calculator. Natural log x, we'll zoom standard just so you can get a sense for what's happening, but it actually has a vertical asymptote at 0. You can get in closer if you'd like, because it's kind of hard to see that on your calculator. You can approach 0 from the right if you would like and see that that happens, but the natural log of 0 does not exist. It only exists for values that are strictly positive. So 0 is the issue, and that is your lower limit in this case. So we're going to take twice the limit as k approaches 0 from the right. And it might matter in this case that we're approaching from the right. It might not. Let's just see what happens as we work our way through this. But either way, the only way we can approach 0 is from the right. The function is not existing for values that approach from the left. You can't approach natural log x from the left of 0. Okay, so we're going to set up our limit, and we're going to then rewrite our integral going from k to e of the natural log of x dx. The natural log of e is 1. That's not the problem. The natural log of 0 is where your function doesn't exist. So that is going to be the issue that you have for this particular example. You should have talked about this integral several times in the integration by parts section. I'm going to remind you how to do that. So to use parts, we're going to let u be the natural log of x, and dv is going to be dx. So this is the way that we work on these natural log integrals. We use parts, and we let u be the natural log function. du is 1 over x dx, and v is x. Okay, so we'll rewrite our integral. I'm going to have uv, so x ln x, and that's going to be evaluated from k to e. I'm going to hold on to it for right now. Minus the integral of v du. Hopefully you've done this enough times now, but when you say minus the integral of v du, the v and the 1 over x part of the du are going to cancel. I'll just write it because why not? I'm writing everything today. And that's going to, we'll simplify that in the next step clearly. X ln x is going to go from k to e and then minus the integral from k to e of just dx. And if you want to skip that particular step because you're kind of like, okay, clearly it's 1 dx, I'm just going to integrate it, that's fine. Just do that. Okay, so you have x ln x from k to e. The integral of 1 dx is just x. And again, that's going from k to e. Just a lot of little small steps here. You could technically evaluate this all at once if you would like, but officially you have x ln x minus x going from k to e. And then we have e ln e minus k ln k minus k. So just using the FTC there with the upper limit of e and the lower limit of k. Now, e ln e is just, well, let's evaluate the limit. Let's pop it off here. I'm going to keep my 2 in the front. As k approaches 0, that's not going to affect this. ln e is 1 times e is e. So you have e minus e. So this is the e minus e minus, and then 0, ln 0. And if you're thinking about this from a limit perspective, sorry, ln 0 is going to be negative infinity in that case. So you have 0 times the natural log as k approaches 0 from the right, which is negative infinity. Remember, we looked at that on the graph. As k approaches 0 from the right, ln k approaches negative infinity. And then you'll have minus 0. So the only thing we need to worry about in this case is technically e minus e is gone. We just need to worry about this indeterminate form. Everything else is fine. The indeterminate form came from this piece. We got a 0 here. No big deal. This is a 0. I just need to focus on this particular integral. I'm going to take the negative sign and I'm going to put it in front of this function. And then we're going to use L'Hopital's rule on it. K ln k. We did one similar to this yesterday. We said that in order to use L'Hopital's rule, we need to write it as a quotient. So I'm going to keep the ln k in the numerator, and in the denominator, I'm going to write it as 1 over k. So multiply by k, divide by 1 over k. Same idea. Write it as a quotient so that you can apply L'Hopital's rule. Now, you're still looking at an indeterminate form here. It's still in the form of negative infinity over infinity. But we're going to simplify this out by taking the derivative in the numerator and the denominator. So the derivative of ln k is 1 over k. And yesterday we talked about the derivative of 1 over k being negative 1 over k squared. Because 1 over k is k to the negative first power. So we did this yesterday in the L'Hopital's rule lesson. And then we'll simplify this again. So you are officially taking the limit as k approaches 0 from the right of 1 over k times negative k squared over 1. So instead of dividing by 1 over k squared, you can multiply by negative k squared over 1. And then you'll get, you can cancel out a factor of k and you'll just have negative k. And then this will just give you 0. Okay, so this piece right here, we took care of down there. This one might be something that you need to pause and look at later, or just pause and make sure that you understand, because every other term here we were able to apply a limit for without L'Hopital's rule. It was this one that gave us the indeterminate form of 0 times negative infinity. And then we went ahead, rewrote the function as the quotient, took the derivative in the numerator and denominator, simplified, and applied the limit. As k approaches 0, the limit of negative k is just going to be 0. So now you can say that your whole limit is 0, because if you were to put this back together again, going back, yikes, down here, you would have twice, and then 0 minus 0 plus 0 equals 0. 0 is still a finite value. That still means that your integral converges. All right, I gotta go pick up the 2-year-old. I got 2 more examples for you. Don't go anywhere. I'm gonna have to splice these 2 together. But I'll be back. 2 more. I've got one with an inverse trig function, and then I have one where you have an infinite discontinuity in the middle of the interval. So stay tuned. Let's stop my recording. All right, so let's finish this up. I have 2 more examples for you. This one is example 7. They're both going to be shorter examples. Example 7 is going to be the integral from 0 to 5 of 1 over the square root of 25 minus x squared dx. So again, this one is not screaming out improper integral at you. It's not something that you would look at and automatically think like, okay, this is terrible. But you're going to look and just verify that the values that are inside your interval are going to work for this integral. So for instance, if I let a be 0, which it is in this case, or I should say let x be 0, the square root of 25 minus 0 squared is just going to be the square root of 25. Actually, the only value in here that's going to cause you a problem is going to be your upper limit. If you let x be 5, in this case, 25 minus 5 squared is going to give you 0, and we can't divide by 0. So that's why this is an improper integral, because you have an infinite discontinuity at your upper limit of integration. So like I said, you're going to have to check that. And we'll rewrite this using a limit. So we'll say that this is the limit as, and pick your variable. No, I'm going to go with k for consistency. Let's say this is the limit as k approaches 5 from the left. I have to approach 5 from the left because I'm going from 0 to 5. So I'm only approaching from the left in this case. Of the integral from 0 to k of dx over the square root of 25 minus x squared. I would like for you to recall that this is a particular form that you should be familiar with. Du over the square root of 1 minus u squared is going to be the inverse sine of u plus c. So we can use that here. Go ahead and rewrite your integral 1 over the square root of 25 minus x squared. We'll pull it outside of the integral for a minute. This will be our side work. So we'll go ahead and pull it outside of the integral. And then we'll try to get our 1 here by dividing everywhere by the square root of 25. So when you're inside the radical and you divide by 25, it's assumed that it's the square root of 25 because it's under the radical. So you'll have 1/5 divided by the square root of 1 minus, and then take the square root of 25, and you'll get x over 5 quantity squared. When you square that, you get x squared over 25. And then you are ready to go We have the limit as k approaches 5 from the left. And this time, you know what? I'm going to move this over a little bit, actually. Because I want to be able to put my 1/5 in front of my limit. So I'm going to do that first. So we have 1/5 times the limit as k approaches 5 from the left. There's the 1/5 that I put in there. Of the integral from, let's see, we'll call it dx over the square root of 1 minus x over 5 quantity squared. Excellent. And then we'll just do a u substitution here to simplify this out. So we'll let u be 1/5 x, and then du is 1/5 dx. 5 du is equal to dx. So the 5 and the 1/5 are going to cancel out. The limit as k approaches 5 from the left. And then we have the integral of du over the square root of 1 minus u squared. And that's going to be the limit as k approaches 5 from the left of the inverse sine of 1/5 x. And I almost forgot that I didn't put limits on this from 0 to k. All right. Now we'll go ahead and evaluate this using the FTC. This is the limit as x approaches 5 from the left of the inverse sine of k over 5 minus the inverse sine of 0. Now the inverse sine of 0 is 0 because the sine of 0 is 0. So that one is going to go. What you're worrying about now is this one. And when you evaluate the limit, you get the inverse sine of 5 over 5, which is the inverse sine of 1. So you're asking yourself, what angle has a sine value of 1? And that angle is pi over 2. So we would say that this integral converges. All right, so that was just another example using an inverse trig function. I thought it would be helpful to see that because we don't do a ton of them. But yeah, and again, just being able to recognize that you have an improper integral when you have one is a really important skill. Just something to look for. This one was slightly more obvious because it was one of your endpoints that actually had that infinite discontinuity. The upper limit of your integral was the issue there. Let's do one more example. And in this example, we're going to do one where the infinite discontinuity is actually inside the interval from a to b. So this will be example 8. This is the integral from 1 to 3 of 2 divided by the quantity x minus 2 to the 8/3 power dx. Okay. Notice here that if you're actually looking at your upper and lower limits of integration, you're not going to see any infinite discontinuities. If we let x be 1, that's fine. We're not getting 0 in the denominator. If I let x be 3, again, not getting 0 in the denominator. That's not the problem. The issue occurs when x equals 2. When x equals 2, f of x is undefined. What that means is that this function is going to have a vertical asymptote at x equals 2. And that would be an infinite discontinuity. So what we're going to do is we're going to set this up so that we're summing up two integrals. But notice that it matters greatly that 2 is in between 1 and 3. Now, if I asked you to integrate this particular function from, for instance, 3 to 5, no big deal, because the infinite discontinuity wouldn't occur between 3 and 5. It occurs at 2. But 2 is inside this interval. That's why it matters. So just because your function has an infinite discontinuity does not necessarily mean it's an improper integral. It's really important to check and verify that that infinite discontinuity is somewhere in between or at one of the endpoints of your limits of integration. So we're going to split this up at 2. I'm going to rewrite this so that we're taking this integral from 1 to 2. I'm going to leave the 2 in the numerator for right now. And then we're going to add that to the integral from 2 to 3 of the same function. Sorry, let's go ahead and set up these two integrals. One of them is going to go from 1 up to this infinite discontinuity at 2. So that means what we're going to do is we're going to set up this limit and you pick your variable. I'm going to go from k to 2, and I'm going to approach 2 from the left because I'm going from 1 to 2. The only way I can approach there is from the left. And then I'm going to take the integral from 1 to k of 2 over x minus 2 to the 8/3 dx. Then I'm going to add that to the limit as I'm going to pick m. I'm going to send m off to 2, and I'm going to approach 2 from the right because when I'm going from 2 to 3, the only way I can approach 2 is from the right. And then I'll look at this integral from m to 3. And then nothing else changes inside your function. So this is really just a combination of the last couple of examples that we've done. Once you split it up, it just looks like basically two of the same thing, if that makes any sense. So when you split it up, it does matter where you split it. We strategically chose 2 because that was where the infinite discontinuity occurred. And then we were just combining the rules for infinite discontinuities at the endpoints of your interval. All right, now we're going to work on the integral. So if you want, I would rewrite these if I were you. So I'm just going to put the 2 in front. And then when I rewrite the integral, I'm going to write this as x minus 2 to the negative 8/3 power in both instances. So now the 2's are no longer in the numerators, they're in front of your limits. And now you have the negative 8/3 power so that you're set up to just do a standard U substitution using that power rule for integration. So since you're going to be doing a U substitution here, it should be pretty clear that your du is just going to be dx. But remember, if u is x minus 2, du is just going to be dx in this instance. All right, now go ahead and integrate. So we're going to increase the power by 1 and divide by the new exponent. So negative 8/3 plus 3/3 gets you to negative 5/3. And when you divide by the new exponent, you're multiplying by negative 3/5. Don't forget, we're still taking that from 1 to k. And the same integral is going to work in both instances. Okay, so now you've integrated each piece, and once you've done that, you can go ahead and apply the FTC in both of those terms. So we'll have twice the limit as k approaches 2 from the left If you want to even move the 3/5 out, you can. If you want to leave it, that's fine. I might just move it out because I want as few things as possible that are kind of complicating what's happening inside my limit. So I'm just going to say this is negative 6/5 when I multiply it in. And then I'll have k minus 2 to the negative 5/3 minus 1 minus 2 to the negative 5/3. And I'm going to do the same thing for this term. This time I'm going to have 3 minus 2, say 5/2, sorry, it should say 5/3. Got it chopped off there. To the negative 5/3, and then minus m minus 2 to the negative 5/3. And then we'll go ahead and evaluate those limits. If you find that it's more useful to think about this limit having a positive exponent, then go ahead and switch it out as k approaches 2 from the left of 1 over k minus 2 to the positive 5/3. And then you can go ahead and apply the limit here, or you can just simplify. Up to you how many steps you want to do this in. But either way, it's going to be 1 over and then negative 1 to the positive 5/3. How did this become a 5/2? I don't know. I did that twice, apparently. Sorry. So it's going to be negative 1, and then when you move it down into the denominator, it becomes a positive 5/3 power. And again, the way that you write this can really vary. I'm just including extra steps. All right, so you'll have 1 to the positive 5/3, and then minus 1 over m minus 2 to the positive 5/3. So I haven't actually even applied the limit yet. At this point, all I've done is just simplified the information that was currently in the expression. All right, now I can go ahead and apply the limit. This one is going to be a constant. This one's going to be a constant, so I don't need to worry about it. I'm taking negative 6/5 times the limit as k approaches 2 from the left. So be careful here, because as you are approaching 2 from the left, you might find that the value here for your function is I mean, you need to consider whether or not you're dealing with positive or negative infinity. Maybe I should say it like that. So we're looking here at 1 over 0 to the 5/3 minus, and then negative 1 to the 5/3 is still going to be negative. You can pop that into your calculator if you would like. Negative 1 to the 5/3 is indeed negative 1. So 1 over negative 1 is still negative 1, minus negative 1 gives you positive 1. And then you have minus 6/5 times 1 minus, and then do the same thing here. Send m off to 2, and then you are, in this case, looking at 1 over 0 to the 5/3. And then we'll simplify. And then you will end up getting, this guy will go off to infinity, as will this one. So it doesn't even matter what happens to your other two terms. You're going to have negative 6/5 minus 6/5, and then minus infinity, and then plus infinity. Either way, you're going to end up in this situation. Oh, actually, you have minus infinity. Negative. Oh, yes. Hold on. You know what we should do? We should look at this function. 1 over x minus 2 to the, we're looking at it to the 5/3 power. We got to fix our sign issue here. All right, as you're looking at this function, as you're approaching 2 from the left, your values are actually approaching negative infinity. So we should really account for that in your sign for infinity here. So this was our approaching from the left. We should actually be looking at negative infinity in this case. And if you're not sure why, consider the fact that you're going to be approaching here for values that are less than 2. So this quantity is going to end up giving you a negative in front of your term. As you approach 2 from the right, you're going to be approaching here, and your values are going to be heading up towards positive infinity. So let's go ahead and correct this sign. The negative 6/5 can stay. That negative 6/5 can stay. But this will be negative 6/5 times negative infinity, which will give you positive infinity. This one stays positive infinity. So you'll have a negative times a negative, which again gives you a positive. So you end up getting positive infinity. You should not end up getting some weird situation where you have infinity minus infinity and then somehow saying that that results in 0, because it doesn't. So be careful there and look at your signs. If you get to the end and you realize, like, wait a second, I have infinity minus infinity, that's an indeterminate form, and you can't have that. So make sure to double check. If you need to, look at the graph. So what I did was I just entered this function 1 over x minus 2 to the 5/3 because I knew I was taking the limit of that function, and then just looked at what was happening as we approach -2 from the left. The y values were approaching negative infinity. And then from the right, the y values were approaching positive infinity. So it is important to consider that as you're evaluating your limit. So now we would say that your improper integral diverges, which I guess isn't really that exciting of a conclusion. But since you already have so much of this function in here already, think about what you were actually presented with here. You had 2 divided by x minus 2 to the 8/3. If you look at what's happening graphically to the function, you're trying to integrate this over the interval from 1 to 3. And hopefully just being able to eyeball this and seeing what's happening with the graph, it's going to be clear to you that there's no way you're going to be able to find the area under the curve. Because at 2, I mean, this piece goes all the way up, and there's a lot of open space there. And same as what's happening over here on the right of that split. There's a sneeze coming. Okay, maybe not. No sneeze. I don't know. It's whatever. All right, it threatened and then it left. All right, so that's improper integrals. So remember, the things that you're looking out for here are any places where the obvious things that are going to happen are you're going to have upper and lower limits of integration, or maybe one or maybe both that are infinite. So that's going to pop out to you. You're going to know you're looking at an improper integral. No big deal there. The thing that I really would caution you to look out for, especially on your test, because I might not say, hint, this is an improper integral, would be any situation where you're being asked to evaluate a definite integral, and one of the endpoints has an infinite discontinuity, something that's causing your function to not be continuous at that value. Like in example 5, it was 12. 12 minus 12 is 0. We can't divide by 0. In example 6, it was the lower limit. The natural log of x is not defined at 0. In example 7, it was again the upper limit. Oh, we can't divide by 0. And then in example 8, that was the trickiest one. In example 8, the infinite discontinuity wasn't one of the endpoints. It was some space in between. So look out for that. Make sure that you are considering improper integrals when you are not in the improper integrals section, because I know that when we're in this section, we're aware, we're looking for it. We know it's there. But on your test, you might not know. And when I put up a review assignment for you, they're going to be just peppered in there, and you're going to need to make sure that you call those out when you see them, because it's possible that your integral might not even converge at all. I mean, you'll know there's a problem because you'll go to evaluate it using the FTC, and you'll be like, wait a second, this is not right. Then you'll realize you had an improper integral the whole time. So that was 7-7. I'll email you about the rest of the plan, but we're going to do 7-6 Wednesday. All right. Test is scheduled for the 20th, so 20th. All right, but I'll email you. I'm not going to take up any more video time with that. Let me know if you guys have questions. I'll put up a homework assignment for you, and I hope you have a wonderful rest of your day.